No, you can keep it. Study from it. Read the book. Tell me what was so confusing about it that you couldn't understand. Okay? Because you guys have to start using that book as a way to solidify what we talk about in class. I don't have enough time to go into enough detail and give enough examples and say things 15 times like I do in my regular chemistry class, which is what some of you need for it to stick. We just don't have time. There's too much to get through, okay? And they're not going to do that in college. You're lucky if they say it once.
Won't say it at all.
Sometimes, yeah, they expect that you just learn on your own, and they might mention something, but they might ask something where they expected you to do your homework and read the book and learn a little bit on your own. Okay? So, 2C4, the localized electron bonding model, describes and predicts molecular geometry using Lewis diagrams and VSEPR model. So after we do this, we're going to actually be able to do the other stuff that's in Big Idea 2, which is about how molecules stay together in liquids and solids, intermolecular forces, that kind of stuff. But we have to figure out what the geometry of these things is before we can figure out what intermolecular forces hold them together. And we're going to use Lewis diagrams. How many people learned Lewis diagrams before? All right, so I'm going to do a sort of complicated example first, and it should be able to show us a lot of what's going on in this page. SO42 minus, the sulfate ion. Even though this is an ion, the atoms composing that ion are held together with covalent bonds. So we should be able to draw a picture of that covalent bonding in this part of the atomic ion. The first step, what's the first step in drawing a Lewis structure? Count the electrons. What type of electrons? Just the valence, right? We all know how to find the number of valence electrons, right? How do we do it? Okay, some people remember 1, 2, 3, 4, 5, 6, 7, left to right, skipping the D block on the periodic table. The other way to do it would be to write out the electron configuration, pick out the subshells with the highest numbers in front, and count how many electrons are in there. That's another way to tell you how many valence electrons something has. Okay, so we're going to count the valence electrons. So sulfur has 6. Oxygen? 6. They're in the same column. They should have the same number of valence electrons. All right, we get 30.
Plus 2.
But we have a -2 charge. So this thing got 2 extra electrons given to it by some cation. So we're going to add 2 for the charge. And so we have 32 electrons to work with. What do we do next?
Single bonds.
We're going to start by connecting everything with single bonds. But how do we do that? I just go S-O-O-O-O.
Make a cross.
Normally we pick somebody to go in the middle. Pick a central atom.
You just get the pick.
Well, there are some rules. Usually the central atom is either the atom that needs to make the most bonds, so the one with the lowest number of valence electrons, which these all have the same number of valence electrons, so that rule's not going to help. But if one of these had 5 and the other ones had 6 and 7, you put the one with 5 in the middle because it needs to make the most bonds to get to 8 to achieve a noble gas configuration. So we're going to say lowest valence electrons. That's sort of our first rule. If that doesn't help, we might think about can usually put an element with the lower electronegativity. That one usually goes in the middle. Those rules should be good enough with just those two rules to help you figure out what goes in the middle. In general, they're going to be usually whatever thing there's only one of. So in SO4, you put the lone guy in the middle, the S. All right. So we're going to put the central atom and make one bond to each other atom. In Lewis structures, the way we show a bond is with a stick. But what does the stick represent?
Shared pair.
Represents a shared pair of electrons. We also call them bonding pairs. It represents those two electrons that are in the space between these two nuclei that are allowing those atoms to be attracted to each other, right? We talked about it in those diagrams. Okay. So these each represent 2 electrons. So how many electrons did I draw total?
2.
8. 2, 4, 6, 8. 2 for each of the bonds. So then the next step would be fill in the rest of the electrons. But how? What are we trying to do?
Each one of them is an 8.
We're trying to get everybody to 8. Not everybody. Somebody doesn't need to get to 8. Hydrogen. Why does hydrogen not need to get to 8?
Yeah.
Duet.
Because there's a rule. The duet rule. No. That's just to help us remember. What is the reason that hydrogen only needs to get to 2? It's trying to get to 1s2. Its valence shell only holds 2 electrons. Really, we're trying to complete the valence shell, right? We want to fill up that valence shell. And hydrogen, its valence shell only holds 2 electrons. That's the only element that's like that. Everything else, we're going to try to get to 8. That's the term octet rule. Okay? So fill in the rest of the electrons in order to fill valence shells. Okay, but there's also some other rules here. To make things easiest, start with the outer atoms first. The outer atoms are the more electronegative ones, so they're going to be the ones more likely to grab those electrons anyway. Okay? So starting with the outer atoms and working your way to the central atom. So, we've got 8, we got to get to 32. How do we show these extra electrons?
Dots.
Little dots, right? And we always put those dots in pairs. We call them lone pairs, right? Because they belong to one lone atom. They're not being shared, they're just belonging to one atom. So that's a lone pair. Now we're at 10 total. 12, 14. This atom's good to go, right? It's got 8 total around it because the shared pair count both for this oxygen and for the sulfur because they're sharing them, right? So we have 8 on this oxygen. What did I say we were at? 2, 4, 6, 8, 10, 12, 14. Let's fill up this one. 16, 18, 20, 22, 4, 26, 28, 30, 32. Stop. When we get to the number of electrons that we had in our total, we don't draw any more dots. Okay? Right, yes, we can't draw more than the number of electrons that we added up right here. Okay? And then, ooh, there's another sort of sub-rule here. We start with the outer atoms. What if we had extra? What if we were at 34? What would I do?
Take a double bond. Put a bracket and then say like something.
If I have extra and I've already filled up everybody, load them up on the central atom. The central atom always gets the extras.
Why would a molecule have like extra electrons in the central? And how would it hold them?
How would it hold them?
Yeah.
That's a great question. That's actually the explanation of how an atom can have more electrons. You will never have to load up a central atom with more than 8 electrons until you're in the 3rd row or below.
By third row, do you mean like this curve have? Yeah.
Sulfur could have more than 8 around it. Chlorine could have more than 8. Phosphorus could have more than 8.
Why?
Nitrogen, oxygen, and fluorine cannot.
Why?
Why? It has to do with their electron configuration. Yes, in the 3rd row, we're starting to fill in the 3rd shell. There's an empty D subshell that we can put extra electrons in. These elements don't have electrons in that 3D subshell, but it's still there. Remember we talked about how we can excite electrons up to those empty levels? Right? So if we have to put extra ones in there, and the element has a D subshell that's available, we can load them up into that D. Okay? Alright, so any extras go on the central atom. Then there's a 4th step that we didn't have to deal with in this structure, but let's take a look at another one that does. Actually, there's something I'd like to talk about in C. C says, in cases where more than one equivalent Lewis structure can be constructed, resonance must be included as a refinement to the Lewis structure approach in order to provide qualitatively accurate predictions of molecular structures and properties. I lied, it's not that one, it's the next one. Formal charges. How many people learned about formal charges? Probably not. Okay. Formal charges can be used as a criterion for determining which of several possible valid Lewis diagrams provides the best model for predicting molecular structure and properties. Okay, so what the heck is formal charge? Let's talk about that. Formal charge is basically, if we were to think about all these atoms sort of breaking apart real quickly, formal charge would be, okay, how many valence electrons did that thing bring in? And then if I were to bust everything up real quickly, how many would that element end up with? And what I mean bust it up really quickly, if they're sharing a pair of electrons, when I bust it up quickly, one's going to go to this oxygen, one's going to go to the sulfur. Okay? So if I were to split everything up in that way, how would these elements end up? Well, oxygen brought in how many valence electrons? No, each individual oxygen brought in 6, right? But if we break this thing apart and split up this bonding pair, then the oxygen will end up with 7, right? So it'd almost be like that oxygen has a -1 charge to it. It's really gaining 1 extra electron that it didn't bring into the molecule, right?
Why would it take 1 and not both?
Well, if we split these up, if these are shared right in between in the middle, I mean,
Do you assume that they're shared right in between the middle? That it's like totally equal?
well, they're not totally shared in the middle. So you're thinking about electronegativity.
Yeah.
Oxygen's more electronegative, so it's actually shared a little bit more towards the oxygen side. You're right. Okay. This is just a way that I remember formal charge. I just say, what happened if we were to split this thing up and split up all the bonding pairs equally? Lone pairs, they're going to stick with that particular atom. Okay. So what I can do is I can calculate what's called a formal charge. And the way we calculate it number of valence electrons minus half the number of bonding electrons plus the number of lone pair electrons. Half the bonding ones because we're like imagining them being split up between those two atoms.
What's the last one?
Lone pair.
Do you count a pair as one or a pair as two?
Two. We're talking about the total number of electrons here, right? So it brought in 6 electrons, like oxygen did. But now in the molecule, it is going to get half of these bonding electrons, so half of the 2 electrons that are being shared with sulfur, plus the 6 electrons that are in lone pairs that only belong to that oxygen. 6 minus 1 plus 6, 6 minus 7, we get a formal charge of -1. So this oxygen is getting a little bit more electron in this molecule than it has all by itself. So it's almost like it's getting a -1 charge. It's not because it hasn't pulled that electron off of anybody. It's still sharing it, right? But it's almost like it has a -1 charge. Okay, and if you do the same sort of calculation for any of these oxygens, they're all going to have a -1. What about sulfur? How many did sulfur bring in? Brought 6 into the molecule, right? Now, how many bonding electrons does it have? 8, 2, 4, 6, 8. So it's going to get half of those. And how many lone pair electrons? None. So this is going to be 6 minus 4. Formal charge is 2. So sulfur got a bad deal, right? It brought in 6 electrons, and now because it's had to share with everybody, it's almost like it's getting less than what it brought in, right? It's really only getting 4 in the molecule if you consider the shared ones to be kind of half and half. And so this thing has a formal charge of +2. Now when you add up all the formal charges, it should be equal to the charge on the molecule, which it is. -1, -1, -1, -1, +2. That gives us a -2 charge, which is what the charge is on this thing. Okay? Now, formal charge, it says, is a way of comparing different possible structures and trying to see which ones are better. Okay? So there are other ways of drawing the sulfate ion. Here's an example. Oh, by the way, we normally add something to this Lewis structure. If I drew this all by itself, somebody would say, wait, sulfur's got 6, oxygens have 6, that's 30. Why'd you draw 32 electrons?
The bracket.
Yeah, you normally add the bracket, and we say what the charge is on the outside of the bracket, just so everybody knows where we're getting that total number of electrons from. Okay, that only matters for charged molecules. Okay, so this is a possible structure. Now, did it violate any of the rules? We have the right number of total electrons, right? We filled the outer shell of all the electrons. We actually overfilled sulfur, right? But I told you that sulfur is in the 3rd row, which means it has an empty d orbital we can stick those extra electrons into. So we haven't violated any of the rules. You would never be expected to come up with this on your own. But they're saying, if they give you this and they give you this, can we tell from formal charges which one is more likely? Well, formal charges, this is not very good. This is not a very fair sharing of the electrons, right? For the oxygens all to be getting one more than they brought in, and the sulfur to be getting two less than it brought in, covalent bonding is supposed to be sharing your electrons, right? So formal charges, if you can get a structure that has all formal charges of 0, that's going to be a better structure. Okay, in this case, we're not going to be able to get all zeros because the total has to be -2, right? So if they were all 0, our charge would have to be 0, which is impossible. So we're going to have some non-zero formal charges, but let's see if these formal charges overall are closer to 0. Well, this oxygen here looks exactly like the oxygen that I did, right? So it brought in 6. It's got one bonding pair, so we'll take half of those 2 electrons. And it's got 6 lone pair electrons, so this is going to be 7. 6 minus 7, we got a -1 here. This formal charge here looks exactly the same as far as the setup goes, so that's going to be a -1 formal charge as well. How about this oxygen here? Try to assign a formal charge for this oxygen. The numbers are on the left side, it's got the wrong orientation.
You can flip it.
Can I rotate?
Or people don't have, well, actually, no, people watch this, so they don't have to watch it. This is in the talk, but that might not be.
Or can they just watch it
You
like
can
this?
flip it, I'm pretty sure you can flip the orientation.
I hope so.
That would be kind of fun.
There's so many comments on it. Oh, come on. Really, what this equation is saying is let's take the difference between the number it brought in to the molecule. That's the number of valence electrons it started with, right? And we're going to subtract the number it has in the Lewis structure. And the Lewis structure, I put this in parentheses because there's 2 different types of electrons it can have in the Lewis structure, right? Lone pair, which we're going to count all of them just for that element, and then the bonding we're going to split in half. Okay, so what'd you get for this oxygen?
0.
Zero. Why, Kransky?
I did 6 minus 4 half times 4 plus 4.
Correct. It's got 4 bonding pairs, right? So we're going to split those up. We're going to say half of those belong to oxygen, so 2 of them. Half of 4 is 2, right? And these lone pair electrons definitely belong to that oxygen, so that's my 4 there. So 6 minus half of 4 is 2, plus 4. So it has 6 in the structure. It brought 6 in. 6 minus 6 is a formal charge of 0. So that's good. The oxygen basically has what it started with. This oxygen up here, also going to be 0. It's the exact same situation. It's got 2 bonding pairs and 2 lone pairs, so its formal charge is going to be the same as the one we just calculated. Okay, how about the sulfur? How many did it bring in? 6. How many bonding pairs does it have?
12.
12, so we'll take half of 12. How many lone pairs? 0. 6 minus half of 12. 6 minus 6, formal charge is 0. Which we knew it had to be because we had a -1 here, we had a -1 here. If these are both 0, and the overall charge is -2, then the sulfur has to be a 0, right? So actually this Lewis structure is better than the one that I drew because the formal charges are all closer to 0. Okay, again, you will never be expected to draw this one for yourself. But if they ask you to draw it, like on a free response, if they say, draw me a Lewis structure for the SO4 2- ion, and you draw this, and then they say, compare your structure to this using formal charges. Which one's better? Well, this one's better because the formal charges are closer to 0. This one we have, if you kind of take like the absolute value of the formal charges and add them up, we'd have 1, 2, 3, 4, 6 here. We'd only have 2 here. This one has all formal charges as close to 0 as we can possibly get. So it's a better structure. Okay? All right. One other thing it talks about in the outline, it talks about, I think it was in C that I read a little bit too early. Can somebody read part C for me? Mia, thanks for volunteering. You don't have your outline out?
No. You have it, Jack? Which one?
2C4 part C.
2C4 part C. In cases where more than one equivalent Lewis structure can be constructed, resonance must be included as a refinement to the Lewis structure approach in order to provide qualitatively accurate predictions of molecular structures and properties in some cases.
Okay, here's a good example of that. Now let's do this one. O3. First step, how many valence electrons? 18, because each oxygen has 6. 6 plus 6 plus 6, we got 18 to work with. Who's going in the middle? Oh. No choice, right? O in the middle. One bond to each of the other O's. Fill in the rest of the electrons in order to fill the valence shells. So we're trying to get to 8. These all need the octet of electrons to fill their valence shell. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Now we got to start filling in that central atom because he's not satisfying the octet, right? Here's 18. Stop! You dare draw another set of dots down here. Why not?
You don't have them.
We only got 18 electrons, right? I've represented 18 electrons right now. I don't just fill in 2 more because the one in the middle needs the octet. It's crazy talk. Okay, so now that our heart rate is up, maybe we got some blood to the brain, what are we going to do?
Double bond.
Double bond. So step 4, the step that I didn't write, is that if everybody's not filling their outer shell, we might have to do more sharing. Right? So if sharing 1 pair of electrons isn't enough to get everybody to 8, well, hopefully you can convince yourself that if I just move these over, that's not going to help me either, right? It would help this one get to 8, but then this one wouldn't be at 8 anymore. Okay? So I can't just move any around. It's not going to get everybody to 8. I need to share. If I take this pair and I move them and make another bonding pair, I would cross these out. Now is everybody happy? Trick question, they don't have a nervous system. Is everybody filling their valence shell? 2, 4, 6, 8, that one's good to go. 2, 4, 6, 8, the middle one's good to go. 2, 4, 6, 8, that one's good to go. Okay? But is this structure sufficient to explain the bonding in O3? Actually, it's not, because if this was the case, if it really looked like this, we would expect, if we looked at an IR spectrum, we would expect to see two different frequencies, right? Maybe one corresponding to this double bond and one corresponding to the single bond. Remember how the different types of bonds had different frequencies? Okay, but really in the IR spectrum, we only see one dip.
Because I think it's a good chain. The little triangle.
The what?
Well, to be involved in that. Make it a triangle.
Make it a triangle. Ah, some people try to get tricky. Yes, there is a way that you could actually try to draw it where they're all connected, like in a triangle, and you might be able to.
Wouldn't that work?
Yeah, that might. Well, that might work.
I will
It won't work once we start talking about something called hybridization. Because what are the interior angles of a triangle?
Now 60.
60 degrees, right?
Yeah.
There is no way to make a 60-degree bond angle. It's too small of a bond angle. Well, I shouldn't say that. It's not very likely. There are some molecules, cyclopropane would be one, where it's actually in a triangle. There are some molecules that make rings, but you're not going to have to draw those until organic chemistry. Okay. But you will be expected to draw something like this, but this structure alone is not sufficient. In fact, if we do something like measuring the bond energies of these, if the molecule actually looked like this with one double bond and one single bond, we would expect two different energies to break those two different bonds. But in reality, there's only one energy required to break the ozone bond. So one way of representing the fact that this structure is not complete is we draw what's called a resonance structure. We draw the other possibility. I took the lone pair from the oxygen on the right to make this double bond. Why couldn't I take it from the oxygen on the left? I could, right? And then the structure would look like this. These are called resonance structures. These are the two different possible ways of showing the Lewis structure that are both necessary to actually explain the bonding. Now, sometimes when we draw resonance structures, we draw a little double-sided arrow like this. But they're actually trying to get away from that because it's confusing. What does that double arrow imply?
Or
Either or. Interchangeable, maybe that it's going back and forth between these two different versions. It's not. In reality, the true molecule is an average of all the resonance structures. So if the bond on the left is a single bond in one structure and a double bond in another structure, the average bond order is 1.5. It's something a little bit stronger than a single bond, but weaker than a double bond. In fact, sometimes you'll see them draw this. Like that. Where instead of drawing a full double bond in between, they draw a little dash bond to kind of show you that there's a little bit extra bond going on here. But it's not really a double bond in each case. It's something a little bit stronger than a single bond, but not quite as strong as a double bond. Okay? So if you look things up on the internet and people are like organic chemists or something like that, they might draw it like this. But what you guys will have to do is you'll have to draw all the possible structures. All right? You will get lots of practice doing that, both in problem set 2C and in the lab that we're going to start. Start tomorrow. Why not, right? Okay. So I think we did 2A, that's drawing Lewis structures. 2B, what's going on in 2B? Dollar. Tell me what's happened. 2B or not?
And then we're going back.
2C4B.
2C4B, sorry. 2.C.4.B.
The VSEPR model uses a Coulombic propulsion between electrons as a basis for predicting the arrangements of electron pairs around the central atom.
So the reason we draw these Lewis structures is so that we can now apply Coulomb's law, Coulombic interactions among the outer atoms to try to figure out what shape this molecule is going to take. All right, so in order to use the VSEPR theory, back up. What's this last one? Share extra pairs to make double bonds if needed, and draw resonance to show all possible places that double bond could occur. That for now. VSEPR theory. That's an acronym. What's an acronym?
Stands for some large.
It's a word where every letter stands for another word. What's an example? PETA. P stands for people. E stands for ethical treatment of animals. Yeah, they 4 of those left out. People for the treatment, ethical treatment of animals. PETA. Goat. Somebody called me goat. First I was like, hey. And I was like, oh yeah. Stands for greatest of all time. Goat in chemistry. Lindsay's like, no, they did. You're making that up. Scuba is an acronym. Did you know that? Scuba.
Really?
Scuba diving?
Oh,
Is it really?
Self-contained underwater breathing apparatus.
That's cool.
NASA, that's another acronym. National Aeronautics and Space Administration. Okay. VSEPR is an acronym, stands for valence, shell, that's one word. Electron, pair, repulsion. Valence shell, that's the outer shells, right? Electron pairs, when we're doing these Lewis structure, everything's in pairs, bonding pairs or lone pairs, and then repulsion. So we're going to look at the pairs of electrons in the valence shell. We're going to look at how they repel each other to predict what shape the molecule is going to take. And unfortunately, this is one of the big sections where you got to do some memorization. That's part of the reason we're going to do this lab. I'm going to have you actually make these shapes. We're going to make them out of cheese balls.
Are you serious?
Yeah. I used to use styrofoam balls and toothpicks, and you stab the styrofoam balls and you can make these little molecular shapes, but the styrofoam balls are really expensive.
So what do you
They're like ridiculously
like how
expensive.
much?
Like for a pack of like 12 little tiny styrofoam spheres, it's like $5.
Oh my god,
So I'd have to spend like
that actually is crazy.
$60 just to have enough for all of us to do. And then they only last a couple of times because you're stabbing them so many times, stuff like that. Cheese balls, I can get a whole big container that will be enough for the entire class for like $3.50. And added bonus, they're edible.
So we actually need them.
Yes, after you actually make the models, you can eat them.
I like
Not until you actually make them. Somebody one time last year like came up, can we have more? What do you mean? Oh, I ate them all. So we're making models out of those. Ate them all. Punks. All right. So, valence shell electron pair repulsion theory. Who's allergic to latex? Anybody? Okay, don't tell anybody I took these balloons out in class. But valence shell electron pair. What?
You're on
Yeah.
Yeah, but then they have to look this way. That's.
I thought you were gonna flip it.
Oh my gosh, these are like the most gross balloons. I don't know if these are even gonna be. It's a good thing I have good health insurance. Okay, this represents the valence shell of electrons in one atom. That stinks. Pretty good. This represents the valence shell of electrons in another atom. And if I am trying to arrange those around some central atom, which my hand is going to represent, sort of, how are they going to arrange themselves? Well, there's no way I can really arrange them other than for them to be as far away from each other as possible. Because as soon as I start to get these balloons to touch, they push on each other and they move back, right? The valence shells of the electrons are going to work in the same way. Because all those valence shells are negatively charged, if I try to move one set of valence shells too close to the other, we're going to get repulsion in order to minimize, we're going to get them to move in order to minimize that repulsion. Okay? So for two outer atoms attached to a central atom, the shape that they're going to take is just a straight line. Okay? Now, what if I add a third atom onto the central atom? Well, if I try to stick 3 atoms onto some central atom, what shape do they take? Triangle, right? In order to minimize those repulsions, they're going to take a triangular shape.
Would they, if you didn't have, like, if you really had, like, one thing that they're all stuck to, would it be, like...
It would be perfectly flat. Yeah, my hand is kind of getting in the way and making them go up a little bit.
Or would it be more three-dimensional, or it would, like, point out, like, perfect...
Nope, it would be completely flat.
Why?
Well,
Our molecules...
clip these. What?
Our molecules, like,
No, some are 3D. But in this case, I can't, even if I try to move this one up, it's going to push the other ones back down, and they're still going to take that flat shape. The farthest the outer atoms can possibly be from each other to minimize the repulsion of their valence shells is to occupy the points on a triangle. All right? Now, there's actually another way that this sort of shape can occur. Look at ozone. Ozone has 2 outer atoms attached to the central atom, but it also has a lone pair. Well, that lone pair of electrons has to occupy some space, right? And if it's a lone pair of electrons, it's going to cause repulsion of the valence electrons on the oxygen atoms. So I'm going to inflate, I'll try to inflate this black balloon.
Start pulling them apart.
That
Pull
is
it
so
apart.
weird.
You
maybe been in the drawer for a little too long. Oh my god. Oh, it's dead. All right, let's try this one. One of these is going to explode in my face. I'm trying to inflate a differently colored balloon to show you the difference between the atoms and the lone pair. Okay, so this one's going to represent the lone pair on top of the central atom oxygen. The yellow ones will represent the other two oxygen atoms. Okay, I've still got three balloons. They're still pushing on each other, and they're still taking an overall shape. That's a triangle, right? However, when we talk about the geometry of a molecule, there's two ways to talk about it. There's talking about the electron geometry. Factoring all the electrons in here, the shape is triangular. But if I factor in just the shape of the atoms would be my fingers in the middle, the central atom, and these two yellow balloons, what shape are they taking? Well, it's not really a line. If I remove this one, bad example. They are linear, but if I try to stick this one in there, it actually pushes them down a little bit. So whereas you might expect from my Lewis structure that this would be all in a line, the lone pair actually pushes those outer atoms down into a shape we call bent. Okay, so the actual geometry here is going to look like this. And it's the lone pair on top that's keeping those down. How about the sulfate ion? What shape is that? Well, we're going to need another balloon. I'm going to do my best to try to connect 4 atoms to my hand in the middle. Okay, I've got 3 and 3 is a triangle, right? But once I try to stick the 4th in, what's going to happen?
Square. Cross out.
Not bad.
Not bad. It actually sort of looks like a pyramid, right?
Yeah.
1 on top and then these 3 on the bottoms. But there's a different shape that we call this. It's called tetrahedral. There's a reason we call it tetrahedral. Let me draw. So the sulfur's in the middle, right? And then you've got those 3 oxygens that are kind of pointed down a little bit. And you've got the oxygen up on top. Now sometimes chemists draw this thing in a little bit more complicated way, because if I put these balloons back together, this picture isn't perfectly showing this arrangement, because this is a 2-dimensional surface, right? But this is a 3-dimensional shape. So how do I draw the 3-dimensional nature of this molecule? Well, the most I can do is line up 3 of the atoms in a single plane. So if I move it this way, I can line up the atom on top, my hand, which is representing the sulfur, and this atom here, and they're all in the same plane, right? But then we have one sticking off to the left, one sticking off to the right, okay? So if I now rotate this so that that plane that I was just talking about is the plane of the board, this one represents the oxygen up here, this one represents the oxygen over here, but this oxygen that I've drawn over here is sticking out towards us, right? This oxygen back here is coming back away from you guys. So the way that we draw that is we draw a little wedge to represent the atom that's coming out of the plane of the board. And we draw a dash to represent the atom that's going on the other side of the plane of the board. So you will see this sort of wedges and dashes. That just means they're not in the same plane. All right? And the reason we call it tetrahedral is if I connect all the outer atoms here, it's a figure with 4 sides. 1, 2, 3, and the bottom is 4. A 4-sided figure is called
Square.
They're called tetras.
a 4-sided 2-dimensional figure is called a quadrilateral. A 4-sided 3-dimensional figure is called a tetrahedron. So this is tetrahedral because the outer atoms make a 4-sided figure, tetrahedron. Why is it tetra and not quad? 3D. But tetra? Have you ever heard that prefix tetra that means 4? Where? Tetra is not one of our metric prefixes. Hecto, deca, there's no tetra. Decalicious. 10 to the second licious. Now you guys maybe it's because you guys had a deprived childhood and you never got to play the best video game system in existence.
Oregon Trail.
No. Original 8-bit Nintendo. Best system ever.
N64.
There's a game for that. I heard some people say it. Tetris. Who's ever played Tetris?
Ooh.
Why do they call it? Yeah, because that's the first thing you download onto your calculator when you get that programming calculator, so you don't have to.
You get Tetris on? Really?
How do you get that?
This
From the computer.
I'm not going to tell you how, because then that's all you'll be
I'm
playing
gonna
for
Google
the next
it.
5 months. Okay. Tetris. Why do they call it Tetris?
Because they're shapes.
But they all have
They all have 4 blocks.
Every shape in the game Tetris has 4 blocks. There's that one.
Doesn't mean to have 4 sides though.
There's L.
Isn't that this easy?
There's the other side.
This one.
And there's a T-shaped one.
That one.
There's the ones that look like
The
The opposite
little.
of the
Oh yeah, the L ones.
The opposites of each one.
Yeah. Every one of those shapes has 4 blocks. Tetris. So that tetra is a prefix that means 4. So a 4-sided figure is a tetrahedron. Be careful. A molecule with 4 outer identical atoms is a tetrahedral shape. It's got 5 atoms total. But if all 4 atoms on the outside are identical and occupying as much space as they can, it's going to take a tetrahedral arrangement. Okay? Now there are versions of the tetrahedral arrangement as well. Because I could have a shape that has 3 atoms attached to it with a lone pair on the central atom. If I stick a lone pair on the central atom, it's going to take that same overall shape. But that's what we call the electron geometry. If we factor in just the shape of the atoms, the molecular geometry is not tetrahedral. Right? If I were to erase one of these, what's the shape of the atoms that's left?
Are not quite flat, but like bent 3 ways.
It's almost like a triangle that got bent down from the middle, right? Which is like a pyramid. We call it a triangular pyramid. Okay? So actually all of these different shapes have a name that for some reason it makes some sense. Eventually I'll go through and tell you why they make sense. But we're going to do a lab and you're going to kind of discover these shapes for yourself. Okay? That's the lab we're going to start tomorrow. Assuming I can get the cheese balls. If I don't get the cheese balls, you'll draw all the Lewis structures tomorrow. So we'll get a bunch of Lewis structure drawing practice, and then we can use the PhET simulation. The PhET simulation allows to just stick atoms onto a central atom, and it works just like these balloons. They just push apart on each other as much as they can, and they occupy whatever geometry leads to the minimizing of the repulsion of the valence shells. Okay? What else do we have to do in 2C4? combination of Lewis diagrams with the VSEPR model provides a powerful model for predicting structural properties of many covalently bonded molecules and polyatomic ions, including the molecular geometry. The bond angles, we can actually predict what the angle is here between these three atoms. That will be shown in the PhET simulation as well. Relative bond energies based on bond order. That's what I was talking about here, right? So we should be able to tell whether a particular molecule contains double bonds or single bonds, or maybe something in between based on drawing these Lewis structures. Relative bond lengths. Right, so the bond lengths would also be a feature of the order. So double bonds are going to be shorter than single bonds. Why?
Did we do anything with rubber bands where like we had the rubber bands holding things together?
That was related to the stretching frequencies. So let's think about my fourth best friend. Coulomb's law. What would Coulomb's law say about a double bond versus a single bond?
There's more like energy charges. No.
I'm glad that I heard so many different things because that means more people are thinking, right? Coulomb's law says higher charges means more force, right? So higher charges are going to pull those atoms in and make a shorter bond. So if I put 4 electrons in between those atoms, it's going to pull those atoms closer together. If I put 6 electrons in between these atoms, it's going to pull it even closer still. If I put 8 electrons in between the two atoms, it's impossible. I don't truly understand hybridization.
Explain that with Coulomb's law. Is that affecting the
Q's. Yeah.
Not the F?
Well, the force is really going to be related to how close they get together, right?
So then
But it's actually related.
Is everything affected? Because the R value is shrinking because it's a smaller distance, and then the Q's are shrinking because you have more charge, and the force is changing.
It's actually related to this graph that we looked at.
This is the weird one that has a little squiggle at the bottom. Yeah.
Remember I said there's 2 parts to this. There's one part that represents the attraction. There's another part that represents the repulsions. And this minimum is where they're equal, right? Where the repulsion and the attraction are equal, then the atoms aren't going to get any closer or any farther apart. That's sort of what we call the bond length. All right? But this attraction is based on the electrons that are in between those 2 nuclei attracting both of the nuclei together. So if I share more than 1 pair of electrons, then this thing, this is a single bond with a double bond, it's going to be even deeper. Right? There's going to be more attraction with a double bond because there's more charge in between those 2 nuclei. There's going to be a stronger force of attraction.
Why does it mean the radius is smaller?
Because the more force of attraction there is, the harder those
Is that
things are going to
related to like what you drew on the graph?
Now, yeah, it's kind of weird because on the graph, it looks like it's intersecting at a bigger distance, right?
Yeah.
I have to think about that.
Okay.
Sorry, it is misleading. I'm glad you pointed that out. But yeah, single, double, and triple bonds, you're going to get a stronger and stronger attraction. Very good question. Presence of a dipole moment. Oh, this is going to be the fun part. In the lab, we are going to do, we're going to play with this diabolical creation.
Oh my god. What is
bunch of ropes connected in the middle with a carabiner.
A what?
Carabiner. Like for rock climbing or for holding all your keys together if you're a hipster. You ride your bike and you want easy access, right? That's a carabiner. Okay, the carabiner just allows me to take some of these ropes off if I don't want them. Okay, but what we're going to do with this thing is we're going to play tug of war.
Like actual
Are you gonna give something?
No, not actual tug of war, because actual tug of war is boring.
It's gonna be tug of war with like one person having more ropes.
No, it's going to be a tug of war, but you guys are used to only doing one tug of war, linear tug of war.
Oh, so it's
You
gonna
pull
be
this
like
way, you pull that way. That's boring.
different one.
So uncreative. We are going to do maybe a triangular tug of war. So we're going to have 3 people pulling with the exact correct bond angles based on the triangular geometry. We might even do I erased it, tetrahedral tug of war.
Does that mean one person's on
I've
the
done
ground?
it where it's
One-
just been one like circle and like everybody pulls onto it.
Yes, what happens?
I mean, nobody went anywhere.
Nobody went anywhere, and that's actually the key to what we're trying to do. We're trying to figure out if I arrange this tug of war in exactly the way that the molecule is arranged, does it go anywhere? If it doesn't go anywhere, that means the molecule is balanced. When we were talking about bond polarity, I think I showed you how if a molecule was linear, you could have very strong bond dipoles, and yet they could balance each other out. But I think it was when I went to that bent geometry, when I changed the angle and it was more bent like this, then you ended up, those bond dipoles didn't cancel each other out in a certain direction. We ended up with a molecular dipole. Okay, so what we're trying to do with these tug of war is figure out which of these shapes lead to molecular dipoles, polar molecules, a molecule with a negative side and a positive side. All right, so I'll talk more about that when I introduce the lab. F is sort of important. Lindsay, read F.
As with any model, there are limitations to use the Lewis structure model, particularly in cases with an odd number of valence electrons. Recognizing that the Lewis diagrams have limitations is of significance.
Yeah, so a good example of an odd electron molecule would be NO2. When I add them up, nitrogen has 5, oxygen 6, so I'm at 12, I'm at 17 electrons. How the heck am I going to get 3 atoms to all achieve their octet with 17 electrons? There's no way I could do it, right? So there are cases where we can't really draw a great Lewis structure here because we don't have enough electrons to give everybody 8. If that's the case, just do your best. Try to get everybody as close to 8 as you can, and then I would probably follow this rule. Fill up the outer atoms first, and then if anybody gets kind of underfilled, it's going to be that central atom. Because the central atom is going to have the lower electronegativity anyway, right? So the outer atoms would pull the electrons harder, and they're the ones that are going to be filled. Should we talk about hybridization? Sure, why not? We got more class time. You guys need a break? Let's take a quick break before we go.